Hello there. This is the first video I'm going to make on Chapter 2 or Calculus 1, and this is based on OpenStax textbook. So let us get started, okay? So let me get rid of my video first here, we don't need it, and get it started. So what we are going to do is work with these sections in the textbook. Of course, the textbook is the OpenStax Volume 1 textbook, and I'm going to show you the link in right here online. That's the online link, and these are the sections we're going to talk about in this video. So if the video gets too long, you will have maybe more than one video, maybe 2 or 3 videos in Chapter 2. But let's see how much we can cover. The first thing we are going to do is talk about two questions that were answered by calculus. Basically, the foundation of calculus. Calculus is the mathematics of things that move. Algebra and pre-calculus so far were things that were not moving, so you can talk about their structure, their relationship between things. There's lots of patterns that you learn in algebra and pre-calculus. But calculus is about things that start moving. And of course, in nature, everything changes and everything moves. So calculus is really necessary to understand the patterns in nature. So there are two main problems that calculus dealt with. One was the problem called the tangent line problem, and that has to do with the rate of change at a given time. So here is a function that you're familiar with. This function is a linear function you learn in algebra and in calculus and pre-calculus, that this is a linear function. And what we are going to do is we're going to look at 3 intervals. So the input values here 1, 2, 3, 4, and we're going to look at the output values, how the output values change as the input values change. So we're going to find the rate from 1 to 2, for example. So when the input changes from 1 to 2, then the output changes from 3 to 5. So in algebra, you learn that is called the slope of this line, actually, right? So this is a line, and that is the slope of it. This is the graph of this. And when the input values change, the output values change, of course. And the rate of that changing, the values changing, is given by that number. Notice that it doesn't change whether you go from 1 to 2 or 2 to 3 or 3 to 4. The rate remains the same. You see, when you go to 1 to 2, the y values go from 3 to 5. So 2 units of change for 1 unit of change of input value. And then the same is true here. You see, from 2 to 3, we go from 5 to 7. From 3 to 4, we go from 7 to 9, and so forth. So you see, the rate doesn't change. So if I ask you, what is the rate at 2, then that's a kind of a weird question, because how can you talk about the rate at one point? And that's the idea that we're going to deal with in this chapter. And then we're going to learn how calculus actually resolved that problem. So in algebra, in order to find the rate, we have to have 2 points, of course. And then you learn in algebra that's y2 minus y1, right? And the y2 here actually is what? The function value at 1, the function value at 2. So you subtract them and then divide by the difference of the x values. And we get 2. And the same is true here and here. Now, so if somebody asks, asks us to find the rate at 2, we can say, well, since the rate doesn't change, we can assume that the rate at 2 is also 2, right? So let's say you're standing at 2, right? At time 2, you're standing, and at time 2, a car with this rate passes by. So at the time that the car passes by you, at that point, how fast the car is going? Well, 2 units per 1 unit of time. So let's say, whatever, number of feet per second, 2 feet per second maybe. But this function is not linear, and if we do the same thing for this function, we'll see that the rate actually changes. You see, the rate from 1 to 2 is 3 over 1. The rate from 2 to 3 is 5 over 1. And the rate from 3 to 4 is 7 over 1. So in this function, since it's not a linear function, the rate actually changes. And of course, the graph of this function is a curve and is a parabola. All right, now, in this case, if somebody asks us, what is the rate at 2, then it would be difficult to answer, because coming to 2, the rate is 3, and then going out of 2, if you think of it that way, the rate is 5. So is the rate 3 or is it 5, right? Or is it something in between? We don't really know. So this is the idea that we're going to deal with in this chapter. So I just talked about that already. You can read it. You see the rate is here not changing, and rate is here is changing. So for a linear function, we call that rate from a point to another point slope. But for all other functions, including linear functions, we can have more general name for them. And that general name for a rate from a point to another point, from one value of the input to another value of the input, we call that the average rate of change. So the average rate of change, the average rate, is given by that number. Like if I tell you that I went to San Antonio and it took me from Houston to San Antonio, it took me 4 hours, and you know that there's maybe 200 miles from here to from Houston to San Antonio, that means my average rate of change is 50 miles per hour, right? So that's the average rate. But if you ask me, if I ask you how fast I was going, maybe at an hour after I started, well, we don't know. So that would be the instantaneous rate, right? All right, so, and we talked about all that already. So how do we make sense of this? Well, let's see. Let us use a calculator. We don't have calculus, right? So the only thing right now we have is the calculator. So we don't have calculus yet, but we will in this chapter. Well, let's say, can we do something about this finding the rate at 2 using algebra, not calculus? And the answer is yes. So the idea is this. You see, suppose we have a function that is increasing like that, and here is, let's say, 2, right? So this is 3 right here. So if I connect these two and find the slope of this line, right, that would be the average rate of change. So obviously, if the point is away from 2, too far away, then the rate probably has changed, since the object has moved from 2 at time 2. So what we can do in order to get an estimate of what the rate is at 2, we can go to a point really close to 2. Maybe go to like 2.001 or another 0, maybe even closer, right? And then find the slope or the rate of change from 2 to 2.0001. How do we do that? Well, we can use a calculator. Use a calculator to do that. Let me wait for it to open. So what we can do is we can put the function, let me do that. So I'm going to put x squared plus 1 in y1, and then I'm going to go to home screen right there. Then I'm going to basically find the difference between, I'm going to find the difference between f of 2.0001, right, which is the y value for this point. How do I do that? Well, I could just parentheses, find y1. y1 is on y variables and y variables there. So variables, y variables, and function. That's y1. I'm going to press enter and then put parentheses 2.0001 and then subtract from that y, again y, I get y1 parentheses 2. So I need another parentheses there, 2, and then two parentheses close twice, because that's the numerator, so I put the numerator in parentheses as you see over here, right? And then divided by the difference between 2.0001 and 2 is just 0.0001, right? So I'm going to divide it by 0.0001 there. So 4.0001 is my estimate of what the rate is at 2, right? That's the best estimate. Now, if we want better estimate, actually, you could go closer to 2, right? 2.00001, right? But there is no end to this, right, to this process. So with algebra, we can never find the exact answer, right? All right, so this idea of finding the average rate of change has a name in calculus, and we are going to name it the secant line. So what is a secant line? Basically, a secant line is a line that connects 2 points on a curve. Now, we can have a curve like this, and a secant line, intersect a curve at many different points, but we're going to just pick 2 of those, maybe these 2, and then we call this a secant line that those 2 points, right? All right, so a secant line is a point that goes through 2 points on a curve. There are 2 ways to name them. So first, let's use this one is easier. So we're going to call the first input A and the second input value X. So the y coordinate for this input would be f of A, and for that would be f of X. So the slope of this, the rate of change of this from A to X is really a slope of this line, the red one here, which is called a secant line, right? So a slope of a secant line, m of a secant line, is f of X, which is y2, minus f of A, which is y1, divided by X minus A, right? So that's one way to write it. Another way to name it is to name the first input value X, and the next input is X plus H. So this would be f of X, and that's f of X plus H. So the slope of this red line will be given by y2 minus y1 divided by what would be X plus H and then minus X, which is just H, right? So that would be just H. So slope of a secant line is given by these 2 expressions. Either of them actually works, and they both mean the same thing. They mean what? The slope of the secant line, which in turn means what? In turn, it means the average rate of change from this point to this point, from this point to this point. Okay? So let's use that idea to find slopes of secant line. Estimate the slope of a tangent line, the rate of change to f of x at x equals to 1. So the idea is, if we have a, let's say we have this function x squared, right, which looks like this, and then here is 1, right, is 0.1. Of course, the y value of 0.1 is also 1, right? So what we want to do is, what is the slope of a, what is the rate of change at this point, right? Well, we don't know because we don't know calculus, but using this idea of slope in algebra, we go to another point, maybe at 2, right? So that's 4. And then connect these two, right? And then what? Then we can find the slope of that line, which is the secant line, right? The slope of that line. I know it looks a little crooked, but it's a line. So slope of that line, make sure, see if I can straighten it. So what is the slope of that line? Well, I can use a calculator, right? I can put this in y1 just like I just did. So I'm just going to put that x squared there. So let me delete that. Oops. Let me delete this. Come back here. So let me delete the 1 there. So that's x squared. And instead of typing all that in, I could do this. I could go to y equals to, well, let's do this one also. So let me go here, and so what I can do, let me show you what I want to do. So what I can do is this, in order to make it simpler to calculate. So I'm going to use this idea of what? This idea of calling the first one x and calling the next one x plus h. Now here, x plus h. So here my x is 1. So the next point would be 1 plus h. Right? So what I'm going to do, I'm going to use the calculator and put this expression in the calculator, so calculator can find the slope for me. So what I'm going to do, I'm going to put it in y2, and I'm going to put parentheses. I'm going to put y1 again. I'm going to go get y1, right? Then I'm going to put 1 plus, now instead of h, I'm going to put x. So I'm going to put x, and then minus, you get y1 again, and then 1, parentheses close, divided by what the numerator here would be what? Would be x plus h minus x, which is h. Of course, since we call h x here, so this would be x, right? Just to use the calculator, we're going to call h x. Of course, our x value here is 1, because that's where we want to find the rate at, right? See right there? We're given x equals to 1. Okay, so now what I'm going to do, I'm going to go to table, set, and I'm going to change that independent variable to ask. That means the calculator does not create table for me. I decide what value I want in the table. Then I go to table, right here, see second table. And now I'm going to make h be what? Well, notice that if I am, let's see, if I'm over here at 1 and the next point is 2, right? Then what plus 1 plus 1 is, what 1 plus 1, what is 2? Well, h has to be 1, so I'm going to make h 1, and then automatically calculator calculates what? y2 for me. Now, if you don't want to see y1, because we are interested in y2. You go back to y equals 2, go over the equal sign right there, and then press enter to turn it off. Then the table wouldn't have it, would have only y2. So when I'm 1 unit away from x, right, if I'm at 1 plus 1, which is 2, the slope of the secant line is given by that number, 3. Okay? Now, what if I am, instead of 1 unit away, what about if I want to be 1, this is 3 over 2, which is 1.5. So I want to go to the left of 2, right? So I'm going to go to the left of 2.5, right? So here is, to the right of 1.5, because 1 is over here. So 3.5 is in the middle somewhere. So this time I want to be over here. So how far is from 1 to 3 over 2? That's 0.5, right? So I'm going to just put 0.5 here. And you see it's 2.5. So add 1, let me do that again. So add 1 is 3, add 0.5 is 2.5. So that is the slope of the secant line. That's the best approximation for actually the rate at 1. Okay, so that's from algebra. And that's what we get. All right, so let me show you what I mean by this secant line idea. It should open right here somewhere. Okay. So what we have here, this program that I used to create this is called GeoGebra, and I have the link in Start Here page. You can download it. It looks like that, the icon down there, you see it? That's what it looks like. And that's what I used to create this. So you see there's a point here, right? So I can start from any point, and this is x squared, right? So let's say it's approximately 1 here. It's not 1, but it's, let me see if I can make it 1. So when x is, that's, let's see, about 9, about 1. You see x is about 1. And the other point, I can take it to any point on the graph and then draw the secant line. Notice the slope of the secant line here is right there. That's the slope of a secant line, you see it? Right there. And this one is the slope of this red line, which is called the tangent line. Now, basically, tangent line, the slope of this line that is tangent to this point, happens to be that number that we're looking for, which is the rate of change at what? At 1. Of course, geometrically, the computer, of course, cheats in order to graph that. You can never actually graph a tangent line because, well, there is always a, how do you do that? Because there is always a point to the right and to the left you can move. So you don't exactly graph it at this point, right? So we can approximate and say the best estimate for the slope of this tangent line is when this point is really close to what? To the other point. Now it cannot be exactly the same point because at that point the denominator of our expression goes to 0. We can't calculate the tangent line that way, right? The slope of it. So we have to be really close to this, right? So that idea later we're going to call limit. And for now, but that's the idea, you see. You don't have to go to the right of the point. You can also go to the left of the point. That means your h can be negative or positive, right? See that? As I get closer and closer to this point, notice this is slope right here and this is slope right there. They get closer and closer to each other. You see, this one gets close to that actually. So as I move this closer, notice that right now, this is 2.02, this is 2.7. But when I get closer and closer, notice that they kind of get closer and closer, notice? right? So it's almost the same right now, 2.07, 2.02. That's the idea. So let me go back to where we were. And so here we go. All right, so we're going to work more with this idea, the idea of the secant line and the tangent line. So our job is to, in this chapter, is to connect these two somehow, and that connection has to do with something we call the limit. So let's move on. So here we're going to think of the function as a position. So suppose we have a function that gives us a position of an object at any given time t, s of t. So when we find s of t from a point, let's say a to t, so let's say this is s of t, so this is a, and we're going to call the second point t, right? So slope of the secant line is actually the average rate of change of the function. But we know the average rate of position over time is average velocity. So the average velocity is defined to be what? The slope of the secant line from a point to another point. So the average velocity from A to T is given by this, right? So it says so here the instantaneous rate at A is given by this expression, using algebra of course, this expression where t is really close to A, right? Either to the right of it or to the left of it, it doesn't matter. If you move the t really close to A and draw the secant line, the slope of that secant line is basically is an estimate for instantaneous velocity at A. Okay, so that's the idea. Of course, instantaneous velocity doesn't make any sense because oxymoron, right? Velocity has to do with from one point to another point, and instantaneous means at one point in time. So this idea becomes more clear as we learn more in this chapter. But for now, we are connecting the average velocity to instantaneous velocity. So we're going to think of it this way. We say that the slope of the secant line approaches v of A, which is the instantaneous rate at A, when t approaches A, right? So that's the idea I showed you in the animation, right? So if you have this secant line right here, right? And this is A and this is T, right? So if you want to find the velocity at A, which is the slope of the tangent line at A, right? You want to find the slope of that. So the slope of that is given by V of A, right? To find that, what we can do is we have to let T approach A. That means we let this point be closer and closer and closer and closer and closer to A, and then see what happens to the slope of the secant. The slope of the secant changes and it gets closer and closer to a point, to a number, and that number is actually that. Now notice here that we cannot make T be exactly A. If we do that, then this becomes 0 and this kind of breaks and it doesn't work anymore. So when we say T approaches A, T cannot be A, it has to approach A, either from right or from right or left, right? Doesn't matter. In this case, we like, of course, in both directions. We like to the slope of the secant approach this number from both, from right and from left of A. Now, if you think of the first point, if you name the first one A, and then name the second point plus H, right? Then you have to make A plus H approach A. And if you want to do that, you have to let H go to 0, right? All right, so this idea of one variable approaches some number and the other variable approaches some other number is called the idea of the limit. And we need the idea of the limit in order to be able to do calculus. Okay, so this problem was solved in calculus, and we're going to see that in this chapter and the next, in chapter 2 and 3, how this was actually solved. But that was the tangent line problem that was solved. So here is an example. Suppose we have the position function given by that, and we have the we want to find out what is the velocity at 2. Well, we don't know how to do it with calculus, so what do? I use the same trick that I just did, right? So I can do what? I can put this in the calculator. So the function is t to the third power, which I'm going to put as x to the third power, x to the third power. But I'm not going to change this. Well, I change it a little bit because I have to modify the point. Instead of being at 1, right, is at 2. So I'm going to change that to 2. And also the denominator has to be, the other one has to be 2, 2. So y1 of 2 plus x minus y1 of 2 divided by x. Then I'm going to go to table set. This time I'm going to let it start from 0, right? And go by maybe point, how far do I want to go? 0.001, right? So I'm going to go by 0.001 right here. And I'm going to, 0.001, right? So I'm going to make it auto this time. Now, when I go to table, notice that it generates the table for me, and I'm going to go up above 0, right? Now, remember this function, it kind of looks like this, right? It's to the third power. And here is 2. Let's say 2 is here. So I want to go to the right and to the left of 2 just a little bit, right? So I'm going to put some points here, maybe 3 points here, and it's here, really close to 2, right? And then find the slope of those secant lines, right? As I get closer and closer to 2, the slopes of those secant lines, right, get closer and closer to the number I'm looking for, which is the velocity at 2. So let's see, what are those numbers? Well, let me turn off again y1 because we don't need it. And turn it off and go back to table. We're just interested in y2 because that gives us the slope of a secant line, right? So when h is 0, we get h. This is the same as x here, right? Because we can't put h in the calculator, so I just put x instead. Now, when h is 0, it means what? It means that we're at 2, and you can't have that because if x is 0 in the denominator, you get an error. So you cannot find a slope when x is 0. That's an error. But if you're close to 0, let's say h is 0.001, then the slope would be what? The slope would be 12.006, right? If x is negative 0.001, then the slope is 11.994, right? So if you're over here, right, the slope is 12 point something. If you're over here, 11.99 something, right? So this means that, as you see in the calculator right here, right, the numbers are read when you go. So if this is 2, if you approach it from the left, right, then the numbers approach 12, looks like it, right? And if you approach it from the right, then the numbers approach 12 again. You see 12.018, 12.012, 12.006, right? So that idea is called the idea of the limit, and based on that we can say that the velocity at 2 is actually 12. Again, we're going to talk more about this later. Alright, so let's move to the second problem that calculus solved. And that problem is area of irregular shapes. Now we know how to find the area of a triangle, right? We have formulas. We can find the area of a rectangle. We can find the area of a trapezoid. We can find the area of a circle, right? All of that. But these are regular shapes that we have formulas in geometry. How do we find the area of something like this? Well, for centuries, we couldn't do that. So what they did basically, they put a grid on this shape, right? So you can put a grid on it, this, right? And then just count number of what? Number of squares. So I could just count, you see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? I can count how many whole squares I have, and then I'm going to count these as partial squares, right? The little ones here, and then put them all together and get an estimate of the area. This is called the method of exhaustion, and in order to get a better estimate, you can make the squares smaller, right? You can make the squares smaller, and now you have better precision, right? So you count your little squares now, you have better precision, and you can get closer, closer, and closer, and closer to the real answer, which you can never reach this way, right? So this idea of method of exhaustion works, but you can never get the actual answer. That requires calculus. All right, so how do we do that? Let's see. Suppose we want to find the area under x squared, right, from 0 to 1. So the first estimate we can really find, which is really easy, is to think of the y value for at 1. So what is f of 1? F of 1, if we put 1 here, 1 squared is 1. So we can say that the area we're looking for, which is this red area here, is between 0 and 1. Why? Because obviously the area is more than 0, and is smaller than 1 because the area of this rectangle is 1 times 1, which is 1. It's between 0 and 1. Not a very good estimate, but at least it's something. It's better than nothing. How can we make it better? Well, we can divide it into 2 parts. So we go to like 0.5 over here, right, 1/2. And we say, okay, at 1/2, what's that y coordinate right there? Well, that y coordinate is 1/4, because 1/2 squared is 1/4. So what's the area of this little triangle? Well, is 1/2 times 1/4, which is 1/8, right? What's the area of this rectangle? Well, is 1/2 times 1. So that's 1/2. So 1/8 plus 1/2 is 5/8. So now we can say that the area of the red part is between 0 and what? And 5/8, which is closer, right? So it's a better precision. Now, to do this, you can divide it into 3 parts and then divide it into 4 parts, right? And this way you can have what? You can have smaller error, right? See, our error here was that much, now is only this much, then is this much, and then is this much, right? So if we continue with this process, method of exhaustion, we can find what? We can find approximate the area, find an estimate for the area we're looking for, right? So the sum of the areas of the rectangles overestimate the area under the curve, right? So how do we make it better? Well, we can divide it into 10, 20, 50, 100, and so forth. And we're going to do that later in chapter 5. But for now, I'm just showing you this problem that was solved with calculus. So where is the idea of the limit here? Well, the idea is the limit here is that the actual area we're looking for, right? The actual area here is basically you get the sum of the areas of the rectangles, the sum of the areas of rectangles. That sum is an estimate that is going to approach the area of the that we're looking for when you make number of rectangles go to infinity. So when we make the number of rectangles go to infinity, then the sum of the areas of the rectangles approach that number that we're looking for. So that's another problem that calculus solved. So the first problem was the tangent line problem, and the calculus related to that is called differential calculus. And this problem is area problem, area of the irregular regions, and this calculus related to that is called integral calculus. So differentiation and integration, there are two halves of calculus. And we are going to work with the first half first, and then we get to the second half starting at the end of chapter 4 and the beginning of chapter 5. All right, so that's the idea of the two problems. Now, the functions that we work with in algebra, in calculus, pre-calculus, calculus, and calculus 2 are functions of one variables, something like that. So that means we have the input, which is x, and we have the output, which is f of x, right? But in real world, of course, the functions are not like that. We can have a function that has not one input, but maybe three input, x, y, and z. And then we have one output, which is of x, y, and z, right? So this kind of function is a multi-variable function, has one output and three inputs. We're going to wait until calculus 3 to work with these kind of functions. The reason is that these extra variables really just add complexity that is not necessary in order to understand calculus concepts. So we can apply calculus concepts to one variable and then just extend them to more variables. That's why we like to do two of these calculus courses with one variable functions of one variable, and then extend it to or more. Okay? All right, so I'm going to end this video here, so we don't want to make it too long. So this video was basically video on preview of what calculus is all about. So let me get back here and see if I can say bye to you and see you in the next video. Okay, so I see you later.